Hey guys, how's it going? I am recording this video today on Monday, April 26th, and today we're going to talk about section 9.5, the dot product. Last week we introduced our vectors, and what we saw is that we only looked at some of our basic math operations between vectors. We looked at addition, subtraction, multiplication by a constant, and negation. What we didn't do is we didn't touch on anything like our other operations like multiplication, division, or exponentiation between vectors. That's because those don't really have as very obvious definitions like addition and subtraction do have. So today what we're going to do is we're going to look at one of the ways in which multiplication is defined between vectors. There are multiple ways that there are reasons to define different multiplications between vectors. We're going to look at one of the most useful ones here today. The two most standard ways to define a multiplication between a vector are referred to as the dot product and the cross product. The cross product usually comes up a little bit more in calculus related topics, so I'm going to leave that one off for today. Today we're going to talk about the dot product, and we're going to see that it's got some close relationship to some trig ideas here. So let's just define the dot product since it's like actual computation is very, very simple here. And what we want to ask ourselves today is like, how is this helpful? Why is this turn out to be a useful thing for us to be able to do? So in general, when we look at a dot product between two vectors, so I wrote this out in English, it's kind of, the English sentence is confusing, the math is simple. When we take the dot product between two vectors, what we're going to compute is we're going to compute the sum of the pairwise products of the corresponding elements. So if each vector only has two components, like my u and my v right now, then we're going to take the sum of the products of the corresponding elements, right? So A1 and B1 are the two things in the first slot, so we multiply them. We add that to A2 times B2, the two terms that are in the second slot. We take that sum, that's what we're going to get out from the dot product. You should notice that the dot product is written with the same little multiplication symbol that you've seen in the past. This is our dot product that's right there. It's the dot between the u and the v. One important thing to notice real quick before we kind of go ahead and do an example right there is that you should notice that this is not producing for us another vector. This is just producing for us, this is just the sum of the product of two numbers. So you should notice that this is actually a scalar, not a vector. And therefore the dot product is sometimes called the scalar product. We could contrast this with the cross product. The cross product does in fact form a vector on the other end, so it is sometimes referred to as the vector product between two vectors. So you might see the name scalar product floating around out there somewhere. That's just another name for the dot product because the dot product does result in getting a scalar, not a vector, out on the other end. Remember, it's just a number. So let's go ahead and look at an example of a couple of dot products right here. This computation is really, really easy. We just want to make sure we see what's happening right here. When I go ahead and I try and dot u with v, all we're going to do is we're going to take the product of the first two components plus the product of the second two components. Remember that we've got lots of different notations for these guys here. We sometimes use the angle brackets. We sometimes use the ij component notation. Either one is fine. In this case, I can see that 6 and negative 2 are the terms that are in the first slot for each vector. So 6 times negative 2. We're going to go ahead and add that to negative 4 times negative 3, the two terms in the second slot. Looks like this is going to give me negative 12 plus a positive 12 in this case. So it turns out that this one is actually going to give me 0. That's actually a special case for us here, and we're going to ask ourselves, what in general can we tell about two vectors if their dot product is equal to 0? That's a big kind of important question for today. Once we set up a little bit more computation, we'll come back and investigate when should we expect this to happen. This is actually sort of a special output right here from a dot product. And our other example right here, you should notice a really important thing. I'm assuming you're all kind of seeing it right here, which is that these two vectors are not of length 2. There are not two components to each of these vectors here. Now, the way that we've been looking at vectors is we've been considering them to be sort of instructions as to how to get to places in the plane. But what you know is that just as there's a 2D plane, there's also like a 3D spatial place that we could be, right? An x and a y and a z coordinate. So why couldn't there be a fourth coordinate out here as well? So one of the things that the dot product is going to help us do is it's going to help us take a lot of two-dimensional ideas from trigonometry and extend them to more than 2 dimensions, which either seems difficult or impossible. And the dot product, because we're going to deal with vectors, is going to make it much, much smoother for us. So in this case right here, if we're going to just go ahead and compute a dot product again, we don't really have any good interpretation for this yet. We're going to get there today. What I think I can go ahead and do is I can just take the pairwise product of each of the orders or element-wise pairwise groups of components here. So it looks like we've got a 1 times a negative 3 plus a 2 times a 0 plus a 3 times a 4 plus a 4 times a 10, right? So we're adding up the pairwise products of each of the elements. So negative 3 plus 0 plus 12 plus 40. And I'm seeing here negative 3 and 12 is 9. 9 and 40 is going to give me 49 right here for u dotted with v. So we can compute a dot product relatively easily here. It's just some multiplication and some addition is all that we're really doing, right? So I'm confident that all of you guys can just simply compute a dot product if you're given two vectors. That's not really the interesting thing. The reason that we should be looking at this today is to say, why is this the way that multiplication has been defined to be most commonly used between vectors here? What is the use of this that makes this a reasonable definition for the multiplication of two vectors? The other big idea here that we're going to see today, as I just kind of said, is that vectors can represent more general lists of information rather than just x and y coordinates in a plane. And we're going to see that this is going to be important for the features we're about to identify for the applications that we're going to see. So what we're going to do here next is we're first going to look at some features of the dot product, some properties of the dot product. Then we're going to look at our big meaningful computation that we're interested in doing today. We then want to come back and see how does that help us understand why, for example, this is a special output from a dot product here. And then we'll see some more examples that help us understand why do we care to talk about vectors that have more than two components, right? So those are all our things coming up here. So let's identify some properties of the dot product and then see why we care to identify these. So our first couple of properties here are really just indicating to us that dot product as a multiplication does hold most of the properties of scalar multiplication that you're used to. So the first one is the commutative property. To commute is to move around. The commutative property says that we can swap the role of the multiplication within the dot product and that keeps the same value. This says we can do the multiplication, you know, left to right or right to left. It shouldn't really matter. You should notice that in this case, this just looks like me writing a1 b1 plus a2 b2, and instead it looks like this would flip us around to b1 a1 plus b2 a2. Well, we know that a1 times b1 is the same thing as b1 times a1. So it's obvious that this multiplication is the same. Therefore, this vector multiplication, this dot product multiplication must also be the same. The other property that we get from multiplication that also holds over for vectors, you know, for scalar multiplication and for vector multiplication is the distributive property. This says that if we take a vector u and we multiply it by like a sum of vectors v plus w, that we can in fact do the distribution of that dot product right there and get u dotted with v plus u dotted with w. Just like we would get the distributive property for scalars, we get an equivalent distributive property for vectors, and quickly you could give yourself some a's, b's, and c's and very much convince yourself that that guy's going to be true right there. Our big important one for the day today that we're going to use multiple times is that the self dot product, is very closely related to the magnitude of the vector that we saw in the previous video. So you should notice that if I do something like dot u with itself, like u dotted with u, this is something that in scalar land, I would say to you, what's u times u? And you'd say it's u squared. We're going to get something very, very close to that here. You should notice that if u is defined to be something like ab, then it seems like this is really just giving me a times a plus b times b, which is really just a squared plus b squared. And that's almost the magnitude of the vector u. In the previous video, we defined the magnitude of a vector to just be like the length of the vector in two-dimensional space, right? It should be the square root of a squared plus b squared. So you should notice that if we squared this magnitude of u, then we'd get the dot product of u with itself, right? So in general, this is going to, these two pieces of information are going to combine to tell us that when you dot u with itself, it's, as we said, very, very similar to squaring. We're just saying we're squaring the magnitude because that doesn't, otherwise, if you say square a vector, I literally think we'll just take the dot product right there, right? So the squared magnitude is equal to taking the dot product with yourself. We'll take advantage of that one here today. Finally, just because we're listing ways in which vector products agree with scalar products, right? Our vector operation today agrees with regular math operations that you've done before. Any zero vector times any other vector is going to give us 0 as the resulting dot product. And you should notice I did do all my vector notation correctly here. A 0 vector would just be the vector of any appropriate length filled with all zeros. V is any vector at all. If you take the dot product of any vector with a 0 vector, then you are going to get the scalar of 0 because we always get out scalars from the dot product there. So who cares? What can we do with a dot product that we couldn't do otherwise? We're going to build an idea right now in 2 dimensions, and then we're going to extend it to more dimensions to get us out into a place where the trig alone couldn't have handled it and where we needed vectors to be able to help us out. Our big computation idea today that we want to dig into is the angle between any 2 vectors. It turns out that we already have the math that we need to find the angle between 2 vectors if we're in 2 dimensions, right? If we have a 2-component vector, I can just find the angle that any 2 vectors are going to be at, and I could find the angle between them by doing just some subtraction and we're done. However, I might want to be interested in finding the angle between 2 vectors that have more dimensions. And so finding this relative distance between 2 vectors is going to be kind of our big idea for the day. So last week we graphed a bunch of vectors and we also graphed their sums and their differences. And I want to graph, in particular, I want to kind of put together some of these pieces here to graph some of these sums and differences to help us see a nice graphical relationship. In particularly, we're interested in the relationship between the vector u, the vector v, and the vector u minus v. So I'm going to build a bunch of sample vectors on the top of my grid right here and then draw a bunch of them together once we've kind of got all of our pieces, right? So let's start with just some arbitrary vector of u. And so I'm just kind of drawing some right here. I've got like a picture in mind, but it doesn't matter specifically what the component parts of these actually are. So I'm going to pick my vectors to be u here, and then maybe let's give ourselves like a v. So it looks like in this case, u is the vector 2i plus 2j. It looks like the vector v here is 3i plus 1j. And what I am interested in doing is examining the subtraction u minus v. So remember when we did u minus v last week graphically, I said I like to think about this as u plus negative v. That's the easier way for me to think about what that is, because I know that when I do addition of vectors, I just keep on graphing one tip to tail, right? The tip of one starts the tail of the next. So that makes me kind of realize here, I'm also interested in knowing what negative v looks like. Here's my negative v vector. It's the same vector as v, it's just pointing in the other direction here. So it looks like this was really my base for that one, and my tail was on the opposite end right there. Now my next question is, I'm wondering for myself, what does u minus v look like? Well, to find what u minus v looks like, I need to go ahead and do u, then do v. So I'm going to start at this location right here. I'm going to do my u vector. Oh, sorry, I said do u, then do v. I meant to find u minus v. I need to do u, and then I need to do negative v. All right, so there's u. If I then stick on to the end of u, the beginning of v, I now want to go left 3 and down 1. So we know from last week that that u minus v is going to be the very beginning to the very end of whatever we've graphed. There's my negative v. So this must be the vector right there, u minus v. You can see it right there. It looks like it's negative I plus j. So we've built 3 vectors. Now what we want to see is that u, v, and u minus v are always going to be guaranteed to form a nice little triangle. So check out the triangle that we can form when we put a bunch of these guys together here. If I'm going to start at one common place, like right here, and I'm just trying to pick a good space where I'm not going to run into other things. So what I'm going to do is I'm going to graph both u and v from this location right here. So here's my u. Here's my v. Hey, wow, I'm drawing straight lines for the first time. And you should notice that u minus v is this left one, up one. That's exactly what we've got in between these two right here. Here's u minus v. So it is always the case that if you want to graphically do the subtraction between two vectors, then you can always just graph the two vectors that you're subtracting from one common point, and then the connection between them will be the difference in those two vectors, that u minus v that we're interested in right there. Part of the reason why this makes sense to me is because it should be the case that you should be able to add v to u minus v, and you should see that the v and the negative v are going to cancel, leaving you just with that u right there. So that's kind of why it makes sense to me that we should be able to do v first, then u minus v, and if you add those together, oh, excuse me, then what you get is the resulting vector is the very beginning to the very end, which would just be u, because the v and the negative v canceled, leaving you just with u right there. So what our goal here is to discuss what is the angle between two vectors. What I want to know is I want to know the angle between u and v. You should notice that one of the special things going on here is that knowing u and v, we can in fact form a triangle with the side lengths of magnitude of u, magnitude of v, and the magnitude of u minus v. If we did that, then it seems like we have a triangle where we know all three side lengths out here, and therefore it seems reasonable that we could compute the angle in between any of those two sides. So we want to find the angle between any two vectors. Given an arbitrary triangle and all three side lengths known, how do we find the angle between two sides? So go ahead, quick, dig back. You know the answer to this. We just did it a few weeks ago. If I have any old triangle ever, and I know all three side lengths, but I don't know any of the angles, then what is a formula I can use to help me find one of the angles that might be between two of the sides? And you should be remembering here the law of cosines. All right, so here's the law of cosines that we had before. And what we're going to do now is we're going to build a law of cosines statement. But remember, these are vectors that are indicating direction. For example, vector u is not the length of the side length, it's the instruction steps to get from this point to this point over here. What we're going to need to use instead is we're going to need to use a bunch of the magnitude notation with those double bars to indicate the length of each of those given vectors here. So let's go ahead and kind of redraw our picture here that we've got our u and our v and our u minus v. That's the guy that we drew for u. This is the guy that we drew for v. This is what we drew for u minus v. And this is our angle of interest. It's the angle between u and v that we are on a hunt for. So in this case right here, it seems like given that this is going to be the theta angle right here, that means that this is going to have to be our side length c, and this can be like our a and our b, because the unknown angle is always opposite of the side length c. That's right there, right? If that's my theta, that always matches with the opposite side length of c right there. So let's go ahead and start this guy with our c squared equals a squared plus b squared minus 2ab cosine of c, right? Or I should just say, I'm just going to write this as theta since I wrote theta in the picture right there. And there's our theta that we're interested in, the angle between vectors u and v. So this is going to look hairy, but the only reason it's going to look hairy is because there's going to be 1,000 of these little double bar notations out there just to indicate a magnitude. The notation for this looks way worse than the math actually is. So let's go ahead and check out and see what we're going to get. So in our case right here, we need to know this side length c, and we need to square it. And what we know that this side length is the magnitude of the difference between u and v. So it's the magnitude between u minus v. And it's really that magnitude squared, right? Because we want c to be squared. So c is the length of this vector, and we say that the length of that vector is the same thing as its magnitude, which we indicate with those double bars, right? Very, very similar here for a and for b. We're going to call A the u vector, so that's going to be our vector u's magnitude squared, plus our vector v, its magnitude is b, and we want that squared for our formula. We're going to go ahead and subtract off 2 times the magnitude of u times the magnitude of v times cosine of the angle between them. And that's the thing we're really hunting for out there. Now, right away, what I'm remembering to myself is I'm thinking to myself, you know what? I feel like I remember seeing something special about that whole magnitude squared thing that just cropped up 3 times. What is it that I remember here? Well, I'm remembering a minute ago that whenever we wrote a magnitude of something squared, it was really just the dot product between that thing, right? It's sort of like the squaring version with vectors right here. So it seems to me like my new way to write this is u minus v dotted with u minus v should be equal to u dotted with u plus v dotted with v minus 2. Now I don't have a way to kind of like simplify this one because these ones are not squared, but I at least was able to write my 3 squared terms over here all as dot products instead. So this is the dot product of u minus v with u minus v. And so now I'm recognizing that it looks like this is actually a big old multiplication to be done right here. And I'm remembering, again, a second ago, that we agreed a bit ago that we're going to get the distributive property for vectors in the same way that we get the distributive property for scalars. So we can distribute this expression right here. It seems like if I use the distributive property to essentially FOIL this out, what I'm going to get is u dotted with u is first times first. Outer is going to be negative u dotted with v. Inner is going to be negative u dotted with v. And last is going to be negative v dotted with negative v, which should be positive v dotted with v. This is equal to u dot u plus v dot v minus 2 magnitude of u magnitude of v times cosine of theta. Now, so we've written out this whole dang thing as dot products. Here's the things that I'm seeing for myself to help clean this up. One thing I'm seeing for myself is that I have a u dotted with u on the left and a u dotted with u on the right, so I think those can cancel. I also have a v dotted with v on the left and a v dotted with v on the right, so I think those can cancel. Another thing I'm seeing on the left is that my 2 surviving terms here are just giving us a negative 2 right here, negative 2 of them. So it looks like I'm getting negative 2 u dotted with v equals negative 2 magnitude of u magnitude of v times the cosine of theta. Well, we're in great shape now. Now we can just cancel our negative 2's, and it looks like we've just got that the dot product of 2 vectors is equal to the product of the magnitude of the 2 vectors times the cosine of the angle between them. So it is very typical for us then to solve this equation for cosine or even for theta here. So it seems like we could get some statements like u dotted with v over the magnitude of u times the magnitude of v is equal to cosine of theta. Or we could even go so far as to say cosine inverse of u dotted with v over u's magnitude times v's magnitude. Oh my gosh, I messed up writing that down there like 3 different times. Try that again. Magnitude of u, magnitude of v should be equal to theta right here. So all 3 of these are different ways. Like I would refer to any of these as our appropriate formula for the angle between 2 vectors. I've seen books with all 3 of these being like the kind of the final concluding statement right there. But in any event, I don't know. I would say that this guy is honestly the way that I've seen it the most right here. But all 3 of these are effectively equivalent to one another. So what it looks like we can do now is just by knowing 2 vectors, we can always compute the magnitude of each vector, and therefore we know enough information to find the angle between 2 vectors. What am I saying like here? Angle between two vectors here. So let's look at a special case with this formula real quick right here, then see a small example, then see a big example. So special case, small example, big example is what we're interested in here. So my first question is, what happens if two vectors are parallel or perpendicular to one another here? So first things first, if two vectors are parallel, then that must mean that they are pointing in the same direction. And that must mean the angle between them is 0. So we just came up with the formula up here. I'm going to use this middle one right here. And so what I'm knowing here is that the angle between them must be 0. I know that the cosine of 0 is 1, and that should be u dotted with v over the magnitude of u times the magnitude of v. And therefore, it seems to me like u dotted with v is equal to the magnitude of u times the magnitude of v in the event that those two vectors are parallel with one another. All right. Now, on the other hand, I know that if two vectors are perpendicular, angle between them is 90 degrees. So now when I write my cosine of theta equals u dot v over magnitude of u, magnitude of v, I'm seeing here that our cosine of 90 is 0. And then I can even go so far as to do a multiplication by the denominator on both sides. And that's just going to lead me to the statement that 0 is equal to the dot product of u and v. So this occurs anytime two vectors are perpendicular, or we do have a different word for this, it's orthogonal. All right, so dot product 0 is special. If you ever get out 0 from a dot product, then that is a guarantee that the two vectors that you're considering are perpendicular to one another, and orthogonal is just a different math word for perpendicular. It sort of handles, I don't know, lines can be perpendicular. Perpendicular is a relationship between two lines. Orthogonal is a more generic sense of 90-degree angles in math out there. So remember that we got that dot product of 0 from our first example up here earlier. Well, you should notice that if you graph the vector for 6, -4, 6, -4, and -2, -3, that they are going to form a 90-degree angle between the two of them right there. I drew a pretty rough sketch right there, but this is something like our u and our v right there. If you draw a better picture, then you will indeed see that there is exactly a 90-degree angle between those two vectors right there. So where are we at? So as an example, let's go ahead and let's find the angle between two of these vectors. But I want to really remind you, we actually already knew that we could have done this without this formula that we just built. So we're going to do this two different ways, but then we're going to see the real value of this formula is that it works in a way broader context than just being in a two-dimensional plane here, right? So to find the angle between the two vectors, we know that we're going to use the formula cosine of theta equals u dotted with v over the magnitude of u times the magnitude of v. And so I'm thinking to myself, we need three things. We need u dotted with v, we need the magnitude of u, and we need the magnitude of v. So let's go ahead and find them. So u dotted with v, well, to get u dotted with v, I'm just going to do my pairwise product of their individual components and add them up. So I'm going to get 1 from the 1 right there times 3 plus 7 times negative 4. And that's going to give me 3 minus 28. And so it looks like the dot product is going to give me a negative 25 here. That's one piece of information that I needed. The next thing that I need is I need the magnitude of u. And so we know that's like the distance formula with each of its two perpendicular components right here. This should be the square root of 1 squared plus 7 squared, which is the square root of 1 plus 49, which is the square root of 50. And the final piece of information that I need is the length of v, which we're going to find very similarly. Square root of 3 squared plus negative 4 squared. And that's going to be the square root of 9 plus 16. And that's the square root of 25. And I actually know that one. That's just straight up 5 right there. But often, very, very often, you're going to get so many square root terms in this computation, you should just leave them as square root terms. So it seems to me like I can now say that cosine of theta is going to be the dot product, negative 25, divided by u, or magnitude of u, root 50, magnitude of v, 5. I'm actually very, man, for me picking some random numbers to get started for this example here, these worked out to all be really nicely related to one another. I don't even necessarily need to do any algebraic simplification right here. In fact, I'm just straight up not going to. I'm just going to say that our theta should be cosine inverse of negative 25 over square root of 50 times 5. And let's go ahead and go to our calculator and see what we get for this theta right here. So this is one of those ones where you're always going to need to go to a calculator pretty much for these. These very, very, very rarely work out super cleanly. So I've got my Desmos calculator back available to me up top up here. And so I want to know, what is the cosine inverse of negative 25 divided by square root of 50 times 5. And it is telling me 2 point, oh wait, let me double check and make sure. Am I in? Okay, I'm going to get degrees for this guy just to, oh wow, this actually, oh my gosh, did I really pick something that nice? Okay, I literally just randomly selected numbers here. It looks like I picked something that worked out really, really nicely right here. It looks like we're getting this to be 135 degrees right there, according to my Desmos calculator right there. So I did my cosine inverse. I was in degree mode. I got 1.35 or 135 right there. So that formula over here then was pretty dang easy to use. Finding the dot product is easy. Finding magnitudes is easy. Putting it together and doing a single inverse cosine, it's pretty dang easy, right? So those steps right there, I hope that you are in agreement, are overall, individually, none of that right there was really that challenging. But what I do want to suggest to you now is we should have been able to do this without this formula. So let's do that because I want to kind of emphasize the difference here. All right, so what I just want to know is what angle do u and v live at? So our angle u, or sorry, our vector u is the I plus 7j, and v was our 3i minus 4j, 3i minus 4j, all right? So I could think of these as like 1, 7, and 3, negative 4 for my u and for my v. So what I can do is I can just convert to polar, right? we know the formula that we can think of our theta as being the tangent inverse of the y component over the x component. Let's go ahead and see what we get when we just find the individual angles associated with u and with v. And these are relative to the x-axis here, so I'm going to just mark those with theta u and theta v right there. And let's go see what happens in Desmos when we do these computations here. So I'm going to go ahead and do tangent inverse of 7. And I'm getting 81.869. And then I'm going to do negative 4/3. I'm getting negative 53.13. And you should notice that what is the angle between these two things? Well, this guy is going to be up here. This one's going to be down here at negative 53. So I'm thinking to myself, if I did the subtraction, 81.869 minus negative 53.130, then what am I going to end up getting? Well, if you add these two numbers together, since that's really addition, 80 plus 50 is 130, plus 1 plus 3 is 134, and you should notice that these decimal expansions are actually exactly complementary of each other right here, which is that 135 degrees that we're getting right there. So we could have literally just found the angle between them by computing both of their individual angles in polar form and just finding how much angle was between them by doing a little bit of addition or subtraction right there. I guess subtraction in this case, the upper one minus the lower one, which happened to be negative, and it literally gave us exactly 135 degrees right there. Or I guess my slightly better way to show this would be come back over here and let's just literally do it that way, right? Tan inverse of 7 minus that. It's literally telling us 135 degrees exactly. Tan inverse of 7 minus tan inverse of negative 4/3. The fact that equals some really, really, really nice number is kind of shocking right there to me, except that we'd already done the math. We'd already gotten the answer using a different technique. So what's good and what's bad about this? So the good thing is technically you guys were already capable of converting things to polar and doing subtraction. And so therefore you should say, well, I don't need that new formula. I can just do 2 quick tangent inverses and do some subtraction and I'm done. But here's the thing that's really nice. This formula, this tangent inverse formula, only works in 2 dimensions. If you were in perhaps 3 dimensions, there isn't some just take the inverse tangent of these x, y, and z numbers out there. There's not a formula that does that. This up here has no restrictions on the number of dimensions that we're living in. This would have worked out for 1, 2, 3, 4, 5, 6 dimensions. Doesn't matter. Any number of dimensions were good. So what I want to go do now is we should go look at a much more interesting example here that emphasizes the fact that having more than 2 dimensions to live in is very often meaningful, and it matters that we can do this math in more than 2 dimensions, meaning this is not necessarily always going to be our best friend right here because this is very limited to 2 dimensions only. So let me just say this. Very limited. So let's go see a higher dimensional example. So, um, and I guess this paragraph is just saying this. So who cares about the vector formula if we could just find their individual angles and subtract them? Well, it turns out if I were to give you a vector in 3 dimensions or higher, you can't just use the compare the 2 angles version because you don't have a way to compute a single representation of angle given 3 spatial coordinates. However, there's no issue with any number of dimensions in the vector formula for the angle between vectors. So that's always going to be useful for us. So let's go ahead and see. We're going to do a kind of a bigger example here today, and I'm going to give you a written homework problem that's going to relate closely to this. So let's take a look. In our example here, we've got a genetics researcher. So what a genetics researcher is currently doing in this hypothetical scenario, they're studying the presence of 4 different genetic factors or alleles among 3 different populations. The researcher wants to know which of the 2 populations seem to be the most closely related to one another. I'm going to call the four genetic factors lowercase w, x, y, and z. We're going to call the three populations capital A, B, and C. The researcher is going to go to each of those populations, sample a large number of people, or I guess in my mind I'm picturing this being more like bugs or something like this, but I know that this is like a human genetics thing too. And they're going to determine the proportion of people in each population that have each genetic trait, right? So there's lots of genetic traits that only some members of a population have. And we can look at things like, for example, we can often tell if a person has a strong European heritage if they are not very lactose intolerant, right? If you can handle digesting milk, that's a thing that generally belongs to more like European type peoples, whereas more Asian, Middle East people often don't have as good of a tolerance to digesting things like cow's milk or goat's milk, stuff like that. And that's purely a genetic thing. That's like, does your DNA tell your body to produce certain like lactase to digest the lactose that's in your body there. So those are the kind of genetic factors that I'm imagining here. So we're going to sample a large number of people from every population, and we're going to determine the percentage or the proportion of people that actually had that genetic feature, right? And this is all collected after all the sampling was done for all of the genetic factors across all the populations. Here's the final result. So we can interpret this table and entries in this table, such as within population B, 12% of the people that were sampled carried the genetic factor Y, right? So genetic factor Y here was held by 12% of the people within population B. And that was double the number of people that they found it within population C, or double the proportion, and four times the proportion of people that had it in population A. So we can see clearly that whatever genetic factor Y is, it's held much more commonly among people in group B than in groups A or in group C. But you should notice that other features for population group B, it has very few people have the W gene, and many more people in populations A and C have that W gene right there, right? So my question is, based on just these four genes, based on just four genetic traits out of the millions or even billions that we have, which of these two populations seem most closely related to each other? So our answer should be A and B, or A and C, or B and C, right? And so our answer is A and B, B and C, or A and C. All right, our answer is one of those three things. We're looking for the pair that are the most closely related. So what we can do is we can think of these columns for the proportions of each genetic factor observed by a single population as a vector. This is a vector with a four-dimensional vector, a 4D vector. I'm no longer trying to picture something in XY coordinate space or even XYZ three-dimensional space, but I'm just thinking these are four features that belong to each of the populations. All of the populations can have measured each of these four features. And so maybe these are a good way for us to compare these things, right? So I'm thinking that each of these three columns seems like a vector with four components, and then I can do the math to determine what is the angle between column A and column B? What is the angle between column B and column C? What is the angle between column A and column C? And the smallest angle between any two pair is going to be the two most closely related genetic groups out there, which is very cool. So let's go ahead and do the dang thing here. What are we going to end up seeing here? So what I'm going to do is I'm going to write some things out for myself here. I'm going to come up with vectors A, B, and C. And what we're going to do is we're going to sort of like try and do this as smartly as we can by doing like all of our types of computation that are associated with each other together. All right, so first thing we want to do is I just want to write these in like vector component form here. So A had 29, 0, 3, and 67. Population B had 10, 8, 12, 69. 10, 8, 12, 69. All right, nice. And population C had, our proportions of observed genetics of 26, 6, and 66. 26, 6, and 66. So what we want to do is we want to compute the angle between each of these groups, right? Group A and B, group B and C, and groups A and C. So what I've learned previously in the last problem that we did back here is that we're always going to need things like the dot products between two and the magnitudes of every single vector. So what I think we should do now to like keep on just doing like our all the work all together is let's find all three magnitudes of all three of our vectors. Let's find all three dot products between vectors. So I think I can do here that bit of math. I think I can say my magnitude of vector A. Well, we just are going to take a big old square root of sum of squares here. I'm going to get a 0.29 squared plus 0 squared plus 0.03 squared plus 0.67 squared. This is the length of this vector in 4 dimensions. If we were in 4-dimensional space, this is how we'd measure how long you went from beginning to end of your path if you traveled in 4 orthogonal directions in 4-dimensional space out there. I'll go to my calculator here in a moment. Let's go ahead and write up all these guys at least. Our length of vector B is going to be 0.1 squared plus 0.08 squared plus 0.12 squared plus 0.69 squared. And our length of, I should be writing my vector symbols here, our length of vector C, that's going to be 0.2 squared plus 0.06 squared plus 0.06 squared plus 0.66 squared. So let's go to our calculator and let's get all three of our lengths, and then we'll compute all three of our necessary dot products here. So to compute my lengths, I'm going to get a, let's see, I want the square root of 0.29 squared plus 0 squared, so I'll leave that, 0.03 squared, oh, not cubed, plus 0.67 squared. All right, so my first one, and I'm going to keep, I don't know, 5 decimal places on this because I'm not quite sure how much accuracy I need here. 0.7. Oh, sorry, I brought up my calculator for my screen, but not for your screen. There it is. I brought it up there for a reason. 0.73068. Our next one here, 0.1 squared plus 0.08 squared plus 0.12 squared plus 0.69 squared. And I'm getting here 0.71197. By doing a little bit of rounding right there at the end. And finally, our length of vector C. 0.2 squared plus 0.06 squared plus 0.06 squared plus 0.66 squared. I'm getting 0.69484. All right, so I've got my lengths of all three of my vectors. Now let's go ahead and find the dot products between each of the three vectors here. So let me get this back off the screen for one moment here. And let's find A dotted with B. And then let's do B dotted with C. And then let's do A dotted with C. All three of the possible pairs that we could be looking at here. Now, A dotted with B, I'm going to get, let's see here, 0.29 times 0.1 plus, I'm going to get 0 for the second one, so I'm just not going to write that. I'm going to get 0.03 times 0.12, and 0.67 is 0.69. We'll go to the calculator and get our A dotted with B. For B dotted with C, I'm going to get 0.1 times 0.2, 0.08 times 0.06, 0.12 times 0.06, and 0.69 times 0.66. And finally, A with C. A with C, I'm going to get a 0.29 and a 0.2. I'm going to skip the 0, and again, we've got a 0 times 0.06 that I'm going to skip. Next up is 0.03 times 0.06. And then a 0.67 times a 0.66. All right, so let's go hit our calculator with all of these guys here. So I'm getting a 0.29 times 0.1 plus 0.03 times 0.12 plus 0.67 times 0.69. I'm getting 0.4949 for the first one. All right, next up, B times C, or B dotted with C, I should say. 0.1 times 0.2 plus 0.08 times 0.06 plus 0.12 times 0.06 plus 0.69 times 0.66. I'm getting a 0.4874. Last one here, A dotted with C. A dotted with C, I'm getting 0.29 times 0.2 plus 0.03 times 0.06 plus 0.67 times 0.66. And that's going to be 0.502. So we wrote the vectors, we found the magnitude of the vectors, we found the dot products between any two pairs of vectors. Now let's compute length. Now let's compute angle between each group. When I say between each group, I mean between each pair, right? So angle between A and B. Between B and C. Our angle between A and C. So remember that we're going to use the formula here. Cosine of theta equals the dot product of the two vectors divided by the magnitude of the two vectors. All right, so I'm going to get here, this should be the cosine of theta equals vector A dotted with vector B, which we've already computed above, divided by the length of vector A times the length of vector B. Well, I've got all this information already because we're smart and we worked it all out, right? Our dot product of A and B is right here. It's the 0.4949. Our length of vector A, we've got right there, 73068. And our length of vector B, 0.71197. Now we can go ahead and do an inverse cosine. And what are we going to get for our angle? Our angle. So here we go. So we're getting our first angle out here. This is going to be our, oh, let me bring it up right here. Boom. So we're going to do our cosine inverse of 0.4949 divided by 0.73068 times 0.71197. And it's giving me an angle of 17.95 degrees. So, can I interpret what that number of degrees is actually measuring? Nope. But if I compute the same angle for these next two, can I compare the angles? Definitely. So let's go ahead and do exactly that here. So next up, cosine of theta is b dotted with c, which we've already computed up above, divided by the magnitude of b times the magnitude of c, both of which we've already computed above because we were good to ourselves. Did all of our work in one big chunk. So b dotted with c, I can see it sitting here at the top of my screen, 0.4874, divided by the length of b and the length of c. B was the 71197. Can I get this up here? Sort of. And then C, I can see right here, 69484. And let me just write this one up as well right now. Now that we've seen what we're doing here. A dotted with C, we got 0.502. Length of A, copying from this one right here, 73068. And it should be the C is right here, 69484. All right. So let's go back to our calculator here, find some more angles, and conclude our final answer here. So back over here, I'm looking at cosine inverse of 0.4874. The one that stays the same is the 711 is still in there, but now I want the 69484. And so I'm getting a much tighter angle between B and C here. Here I'm getting my theta to be just 9.8586 degrees. Right? Much smaller angle right there. And finally, we can go ahead and compute the last one over here. Just making sure I left all those correctly in there. Yeah, so it looks like for our last one, we'll do 502 as our numerator. And as our denominator, we want to keep the 69484. We want to introduce the 73068. And it looks like I'm getting, an even smaller angle of 8.5979. And so from this, what we can conclude is it looks like two populations that were most closely related were A and C, right? And again, this is something that otherwise is very difficult for us to come up with a meaningful way to compute, right? If you're given just a whole mess of genetic information about a population, or about several different populations, and I said to you, hey, can you figure out based on their genetics who's more closely related to who? What exactly are you going to do, right? And so here, ultimately, what we've done is we have found three vectors in space, and we wanted to say to ourselves, which of those three are pointing in the most similar direction? And it might be the fact that these vectors are not necessarily all of the same length, and these example vectors that I just drew right here are certainly only in 2 dimensions. But the point is, when we get into higher dimensions, when we have systems where we want to consider information of just more than 2 pieces of information, which is like everything in the whole world, then it's one of the ways in which we can go about doing this is by doing finding all of the pairwise angles between any of the 2 vectors in multi-dimensional space, and finding the pair that has the smallest angle between them to indicate that those are the 2 that are the most closely related in that multi-dimensional space that's out there. Turns out there's lots of other small adjustments we can sort of make to this formula to give it sort of like weightedness to it or something. If we think that one of these genetic features is far more important than some of the other ones, we can add some weights to this so that some things are taken into more heavy consideration, some things are less considered. But this is like a really good starting place for a lot of these kind of considerations right here, is just to find the angle between any 2 groups using this formula right here, using n-dimensional vectors. and finding the group that is the least distance between each other. Therefore, the closest relationship right there was A and C. So really interesting things that we can do with this angle between two vectors right here. We want to recognize that in one sense it is related to math that we've previously been doing if we're in two dimensions, but as soon as we're into more than two dimensions, then it's not reasonable for us to go ahead and compute that angle between the two of them. As my last statement for the day, what I do want to say is these degree measurements down here aren't as a standalone thing telling us anything. For me to say, oh, the angle between A and C was 8.59 degrees, that's not like a good meaningful actual measurement of distance between populations, because how would you measure a distance between the genetics of two populations? That kind of doesn't really make sense, right? So the final thing to kind of say here is that individually all three of these angles mean nothing to me. But comparatively, I can look at them, since they are all measuring across the same four axes, genetic factors W, X, Y, and Z, that compared to one another, they do give relative closeness, right? So that's kind of the important thing right here, is that this is a comparative thing really only here, because these angles individually don't mean anything to me, because we're trying to talk about distances between genetics. But when we get groups of them together, we can pick out which are the two most closely related by finding the smallest angle between any two populations that might be out there. All right. So really, really practical usage of this dot product concept right here. But the dot product was a required component of this angle between two vectors computation, which is something that is used in like a huge number of different applications, aside from just kind of like, math engineering type things, like we just did right here. This is absolutely like a biology genetics type of application right here that somehow magically crops up with dot products and vectors and angles right there, which is, I mean, honestly, should be a huge surprise to you, right? So I really, really, really like this example. I'm going to make a written homework question for the week that's going to be associated with this example right here. So be sure to look for that. I want to encourage you, when you go to do that example, you should be thinking of the screen that I've got right here, where I smartly organize all my information, write out all my vectors, find all their lengths, find all the necessary dot products, then put the pieces together in the way that I want to see them. And so kind of realize that you should sort of be doing your work in batches for problems like these. There is, in a sense, a lot of repeat computation, and you should do all the related computations immediately next to each other, so that you're sort of building almost like a table of information here. It just doesn't quite go into a table very nicely, but this is very, you know, a procedural way to go through this here. So that wraps it up for our section 9.5 on the dot product, and I will see you guys for our next topic in the next video here. Have a good one.